Good evening. This is the last session for the last live session for the course of Introduction to Fluid Mechanics. I'll be conducting this session. What we will do is first like attempt to problems from topics which were not discussed previously, and then we shall begin to do some revisions. And if there are any doubts, I will be answering that. And uh, so I will try to summarize what we have learned and uh, leave it up to you from there. Okay, let's first start with this question and uh, solve this. So this is from a topic that we have not really we have dealt it in the last week, but we have not given it attention in detail. So let's see what we have here. Air flows in uh, 8 centimeter diameter and 33 meter long pipe at a velocity of 5.5 meters per second. The piping system involves multiple flow restrictions with minor loss coefficient of 2.6. There is a loss coefficient here. And friction factor of the pipe is obtained from the Moody's chart to be 0.02. So what we have to find is the total head loss of this piping system. So let's first understand what is going on. So we are given a geometry. So we are given a geometry that the air flows in uh, a pipe which has 8 centimeter diameter and 33 meter length. So it's a pipe like this. And what is flowing? Air is flowing. There is air flow inside of this. And what is the velocity of the air given here? 5.5 meter per second. So the dimensions of this is given. So uh, like since this air is flowing through this, and we are not like suppose in real life situations we are not supposed to neglect frictional losses. We are not supposed to neglect losses due to other flow restrictions. And since it is maintaining a particular velocity inside this pipe, we must assume that there is something that is driving this flow. Otherwise, the frictional forces will slow down, and this flow will not take place in a steady state. So there must be something that is driving the flow inside this pipe. So what this will be? This will be a pressure difference. So this pressure difference we calculate it in terms of our head. So it will be a delta P. We can also simply use a length dimension by just dividing rho. Now, what we are interested in how much head loss has taken place. So, if I am like giving a head of delta p by rho g on this left side, and the flow is taken from left to right. At the right side, there will be a reduction in head. Why? Due to the frictional losses. So that's what we are like interested in. And this is a very practical problem because we would always try to know what is the losses occurring in our pipes so that we can optimize the pressure supply. Uh, so how do we go about finding this? Very simple. Our friction factor is given as 0.025. So here we are not using our 64 by RE. So the reason might be because the flow may not be laminar here at this velocity. So 64 by RE is only used when it is laminar. Otherwise, we will have to use some other techniques to find out the friction factor, and Moody's chart is one of them. So, from Moody chart, It's a like well documented friction factor coefficients of turbulent flow. Uh, so from there we can find out our friction factor. It's given. So from friction factor we will get a particular head loss. What else is given? There is also given that there are minor loss coefficient of 2.6. So there are other losses as well. So frictional losses are there. Other than that, some restrictions are there. So what this can be? This can be some valves. This can be some orifices. So there might be some geometrical obstructions in the flow as well. So due to that also there can be additional loss that is incurring while the air is flowing through the pipe. And to quantify that, this coefficient is given as 2.6, and also this coefficient has been defined. Uh, so we will use this to and find out our total head loss. So our total head loss will be from this frictional loss and this minor other minor loss. So frictional loss, how would we calculate? For frictional loss, we have this friction factor L by D. So this is straight from definition. This into our V square. We will put in our values and we will get this frictional head loss. So we know each and every value from this in this formula. D is diameter, L is length, V is velocity. So everything we know. So similarly, we will also calculate each, uh, the other minor losses HL. So how we will calculate that is already given. The formula is already given. So basically, what we have here is V square by 2G, which we are kind of scaling our head losses using this particular unit. So like you can see that this is also unit of length. V square by 2G is also a unit of length, and this is also like where is this V square by 2G is coming from. You can like straight away imagine from your Bernoulli's theorem, we had like three terms. One was P, one was half rho V square, and another was rho G. So if I just scale it in terms of length terms, then this becomes P divided by rho G plus V square by 2G plus. So this is basically division by this factor of rho into G. So in this case, like you can easily see that this delta V by rho G is what I talked about giving applying a pressure at one end. So we are using this second definition here. Since we know the velocity here, we do not know the pressure. We can measure the velocity. So we will be using. We are using the velocity here. So V square by 2G is taken as um, a factor that we are scaling our coefficients with. So this V square by 2G is multiplied by this F L by D. So this F L by D, uh, uh, this is also a non-dimensional coefficient. So there is no dimension attached to it. V square by 2G has the dimension length. So as you can see, the F is the frictional factor which depends on your Reynolds number, as you know, and also maybe the roughness of the pipe. So these are some things that this is dependent on, and also like this coefficient of obviously will also depend on how long the pipe is. If the pipe is longer, then my head loss will be more. So simply there is a linear dependency here. And similarly, there is also an inverse relationship with the diameter. If the diameter is less, the frictional losses will be more. If the diameter is more, the head loss will be less. So we have this factor here, which is like your frictional loss coefficient. So we are getting that from our friction factor, length, and diameter. The similar thing here for minor losses, we will simply put our coefficient here and have this problem. So the values are given again, so we can calculate both HF and HL. Our total head loss will be simply the sum. So working like this, working with head losses, gives us a more friendly way of approaching this problem, like other than just like solving all this, uh, solving it explicitly or doing it in an energy method. This head loss is very intuitive and very like relatable in our practical situations. So suppose like we have a tank which is supposed to supply our uh, fluid, and that tank is kept at a height h. So that's basically the concept. How much above your head should the tank be to supply this pressure? So we will get this head that will be reduced by that thing. Uh, so these are problems that you can solve using friction factors. So yeah, the solution is given here. You can check whether your answer comes up to this. So next, another topic that we have not uh, touched upon is Buckingham Pi theorem. So by Buckingham Pi theorem lets us solve problems like we just did right now. So what we did is basically taken all the parameters into this coefficient and just related our head as this is a length with another length parameter which is v square by 2. So, Buckingham Pi theorem actually just helps us do the same thing with more complex problems, and just like gives us an idea about what parameters we can club together and make something like a factor or a coefficient, and what will be linearly or inversely dependent on the other. So how does this work? Let's see in this particular case how does the Buckingham Pi theorem work. So what are the relevant parameters given? It's given as volume flow rate, density, viscosity, bulk modulus, pressure difference, power consumption, rotation speed, and characteristic dimensions. So what we will do? Let's like make a table and like write all this down. So we mention all this uh, in a column. So Q is volume flow rate, rho is density, mu is viscosity, K is bulk modulus, and this pressure difference delta P, let's say, power consumption, let's say W, rotational speed, say omega, and characteristic dimensions, let's say L. So what will be the other columns? So this will be the fundamental dimensions. So in most of these cases, you can already see the fundamental dimensions are three here. So one is the mass, one is length, and is time. And we will write the coefficients here. For example, Q, volume flow rate. So volume flow rate is basically what's the unit of this is meter cube per second. SI unit will be meter cube per second. So simply volume and rate of the volume. So what this will be in dimensional terms? It will be L3 P minus 1. So we will simply write here 3 and here minus 1. So similarly, rho this is kg per meter cube. So it is mass 1 and L minus 3. Similarly, for this we have unit of viscosity is Pascal second. So Pascal we can have as kg kg meter per second square. This is force divided by meter square and second here. So we can calculate all these things and we will arrive at this, and simply we can put this value. So mass 1, length minus 1. So similarly we can fill this up. So I'm not doing for all of this because in this particular problem it is not really required. So we can fill this up, and uh, now what we will do for like proceeding further is what we want is some parameters to be formed. For example, pi 1, pi 2, and so on. So some pi n. So what are these parameters? These parameters are like our coefficients that we saw in our previous problem. This kind of coefficients, friction factor into L into D. So this is the non-dimensional coefficient. So similarly, what we want is these parameters to be non-dimensional. So how we will do that? We can count the number of dimensional quantities which are relevant parameters. We can count them. So in this case, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Right. So 8 parameters are there. So 8 are dimensional parameters. How many fundamental dimensions are there? 3. Right. Mass, length, and time. So if you have temperatures, then you will have 4. If something else is there, for example, like the quantity of matter, like mole, then you will have 5. If you want to take that separately, you will have 5. So in this case, we only have 4 fundamental dimensions. So if you have 8 dimensional parameters and 3 fundamental dimensions, so what does this mean? So these 8 dimensional parameters uh, have some coefficient attached with each of these fundamental dimensions. Right? These dimensional parameters, they have some coefficient attached with this fundamental dimension. Now, to non-dimensionalize them, we need to come up with the terms which have no dimension attached to it. So how? So let's say we have two lengths. So let's say we have two lengths here, H and L. So these are two lengths here. So if I just do my Buckingham theorem with this, so what will be there? So H, L is there, and only one uh, fundamental dimension will be the length. So it's 1 and 1. So in this case, dimensional parameters is 2 and fundamental dimension is 1. So how many terms can I form? I can form only one. So what I will do, I will use this L this coefficient and put that in my H and see what is the value that I am getting. So you can easily see in this particular case it is H by L. So similarly, if we can perform this exercise uh, using all these parameters, and we will come up with this non-dimensional parameters. So how many parameters do we have to eliminate? In this case, we have to eliminate one parameter, and then we could get our non-dimensional. Here we have to eliminate three parameters. If we eliminate three parameters, all our terms that we will we can get can be converted to a non-dimensional form. So that's why the the number of non-dimensional parameters we will get is 8 minus that will be uh, 5. Okay. So these 5 terms. So this is basically our n. So n is 5 in this case. So these 5 terms, what Buckingham if we use this Buckingham pi theorem, then what we hypothesize is these 5 terms are related. So we can have something like some one of these terms as our pi n. This is a function of the other terms, pi 1, pi 2, and so on till pi n minus. So this is our coefficient that we can measure for a particular set of pi 1, pi 2, and till pi n minus 1, and we will get a pi n. So if our parameters change, we need not to be considered about each of the dimensional parameters. Just if we see that these non-dimensional parameters are changing, then only we need to change this particular coefficient. If the non-dimensional values are not changing, even if the dimensional ones are changing, then this particular factor will be same. And also something that we might need to prove out of this pi n can be achieved. So, for example, in our case of frictional loss, we have this HF, this friction ion loss, and we have this parameter V square by H. So this is a non-dimensional number, HF by V square. So what is this a function of? This is a function of, let's say, what to use here? Let's say I'm using P. Okay, so this is simply a notation. It has nothing to do with any physical quantity like pressure. So this is not pressure. I'm just using this as an example. So this is a function of different other non-dimensional parameters like L by D. So that we multiply with our Darcy's friction factor and other things like our Reynolds number, which is again a non-dimensional parameter, and the roughness coefficient, which is again another non-dimensional parameter. So what we have hypothesized here that the quantities that are affecting our pipe flow, we have made a list of dimensional parameters, and here we can use this Buckingham pi theorem to come up with the non-dimensionalized version of these parameters, and we have constructed a function out of it. And using this function, now if we can prepare a chart, for example, like our Moody's chart, then we can have this functional value, and we can solve a lot of problem just by establishing this functional relationship. Okay. So, so next, what I wanted to do is if there is any doubts from any of the previous sessions or the entirety of course at this point. Uh, I wanted to discuss this, but since no one has joined here, so I will give a brief summary of uh, what are the some of the important topics that we have discussed. So mostly I will again touch upon our Reynolds transport theorem, and from that Reynolds transport theorem, what are the different things that we I will try to draw some tangents and touch upon some other topics as well. So I will do the like momentum part of it. So so what is so what we are actually interested in? So the course is titled as Fluid Dynamics. Introduction to Fluid Dynamics, definitely. So when we are studying dynamics of something, what we want to do is basically uh, calculate the actions, the results of some active forces on on some on some system. So, for example, when you have just studied your particle dynamics, what we did, we used our equation of like second law of motion from like Newton's second law of motion, and we have applied it on particles, rigid bodies, to uh, get its motion, how it will move, and like to understand uh, what the dynamics would be. The similar thing we are trying to apply on a fluid. The problem with fluid is kind of like a continuous media when we are seeing in a microscopic scale as we do in our everyday life. So we had discussed about our Knudsen numbers and all. So we had like discussed mm, when we can consider our fluid as a continuous media. So it's generally composed of molecules, and these molecules are moving randomly, and they will collide with each other. And we are so there will be a length scale attached with this phenomena, which is called the mean free path, which is the average distance a molecule traverse before having a collision. So we define the non-dimensional parameter like this, where L is our characteristic length scale. Is basically the length scale over which we are uh, concerned. Yeah. So we were discussing some I discussed two problems and like related to I will just recap. So one related to the uh, friction factor, and like how we can calculate head losses and all. And then we were discussing about Buckingham pi theorem, and we have solved a problem like this. So you can like check the recording, and if you have any particular doubt, then you can ask. So basically, today's session is the last session, and it is like meant to be a summary session or a doubt clearing session. So if you have any like doubts, you can ask. Hmm. Otherwise, like I was giving, trying to present the summary of this course and what we have learned, the, uh, some of the basic concepts that we have discussed. So, if you have any doubt, then we can like proceed to that step.
Continue, sir.
Okay, all right. So, let's then continue. Then yeah. So so for a fluid medium in our macroscopic scale, it's a continuous media, and we cannot simply apply our Newton's second law there. So we need to deal it in this continuum state. So that's why we have studied an approach towards looking into the fluids, which is the Eulerian. So, so Eulerian approach, what does this help? It helps us to map our like kinematic variables like velocity and all to a spatial sense. So we do not attach velocities to every particle. Instead, what we are doing, we are attaching velocity to a particular point in space. And what we want to now study is basically evolution of the velocity or like any other kind of other parameters that we eventually have come across, uh, like by solving our dynamic equations in an Eulerian sense. But our fundamental equation is still our Newton's law of motion. So what we have to do is basically transfer this Eulerian approach. We have the velocity and other parameters. So this these Eulerian variables, we have to transfer it to our Lagrangian sense, which is the particle-based thing where we have our equation of motion F is equal to m. So, so what we have defined is we have defined a uh, control volume. So we have defined a control volume like a system. So what is this control volume? It is basically a space, a fixed region in space into which some molecules may come and it may leak. So it is a continuum like a medium we are assuming to be continuum, but like we do not really what we are currently we are concerned about, there is a fixed region in space and particles may come in and get out however they want, and what we want to track is this flux, and what we want to calculate is how the velocities of the particles inside this region of space change with some applied force. So for this we need use our Reynolds transport theorem. So Reynolds transport theorem, I'm like means for the momentum part, I am like simply stating it. I'm not like going into the details. So here, in if we are doing it in Lagrangian way, what we would have done for a particle, we would have calculated our d, d ddt of mv, right? Momentum. So differential of your momentum. But we cannot do that here because it's a continuous state, and also my particles are coming in and like getting out. So we will divide it into two parts. One is definitely the change in momentum of this like this whole volume. So whatever particles are there inside, with time, how their momentums are changing. So that can be defined as a partial derivative with time, this momentum integrated volume. So how did this mass change into my density? So because at every point my density is now defined. Since it's a continuous media, I do not have mass of every particle. Instead, what I have is density. Density at every point. So instead of mass at every particle, we have density at every point. And this we can integrate over the my entire volume to get a like mass of the whole region. So similarly, if I multiply rho into v, so each rho and v are defined at every point, and how it is changing with time, and I integrated over the volume, so I will get the change in momentum with time across this whole volume. But this is not exactly ddt of mv. Some momentum is also getting in, some momentum is also getting out. For that, we have another term. What is the term? Like, so I will use this notation. So this is basically the surface of this particular volume. So uh, this is our momentum, and we have the flux, outward flux uh, of from this particular region in space. So v dot n, what does this n cap? What is this n cap? N cap is basically an outward normal, unit outward normal. So this is equal to my force, and this we have what we have done is simplified using our Gauss theorem of like the mathematical Gauss theorem. So what we have done is converted this area integral into a volume integral and merged them. So what this will be, dn, this basically becomes So this whole thing in this. So you like know this and you have studied this a lot of times in this course. So so this I will like fast forward. So what is this? This is basically like converted. It can be converted into your material derivative, and you can see there are two portions actually. One is that rho dvdt that we are more familiar with in this setting, and another will basically uh, turn out to be zero due to our continuum due to our continuity equation. What is continuity equation? This is basically conservation of mass. So we must also take into account that the mass is conserved. So basically, the mass that is coming inside, mass that is like leaving, and any mass that is generated inside during this process. So this whole thing so any mass that is like the density is changing inside, so the whole thing, the sum of the whole thing will be zero. So if we take that into account as well, so this will simply reduce to my volume integral of rho dvt. And this is equal to my force. So I have not touched here. I have not touched here so far. So now I will talk about this force. If you have any questions, like this is a summary class. So like and the doubt clearing class as well. So if you have any doubt, so that will be my first priority. So I will answer that. If you do not have any doubt, then I will like do this like summary. Okay. If you have any doubt, please like ask. So this is the last session of this course. You can ask any doubt. Okay. So I'll continue. So this force we have two types, right? Which can act on this control volume. One is body force, and another is surface force. So body forces are we can deal it very simply. Like for example, gravitational force. It is simply rho into g across the whole volume. So dv integration across g. So this is my body force. If I am talking about gravity. If I am talking about electrostatic force, then simply I will have charge density instead of mass density and my electric field. And this will be integrated again over my whole volume to get this body forces. So these are easier to deal with. What about the surface forces? So surface forces, there are a lot of nuances about it, and this is actually where our like fluid portion of this whole approach comes into the picture. So far what we have done is equally applicable for like solids or any form of matter in fact. So now when we are starting to talk about surface forces, here when like the fluid surfaces interact and produce some stresses, and those stresses when we are quantifying, we will get some things which are valid only for fluids. So how do we deal with surface stresses? So if we have a surface, what we define is that a particular area. So like we define like pressure, you already know about pressure. Hmm. So similar to that, we may have a traction force which is like a generalization. So we may have a force which is acting on the surface. It may not be normal to it, and this is like a traction force. And this traction force is acting per unit area. So this same thing we have converted into our concept of stress. So what we use is a index notation here, sigma ij. So ij basically one index denotes the direction of the surface, which is the normal direction of the surface, and another index denotes my direction of the force. So that's why two indices are required. So this is the second order tensor. So this is my total surface force, how much is acting. So this will the stresses can like give me the idea. So what I will write in this right hand side of this equation, I will write, I will simply write sigma ij. So this is a tensor. So this will be dotted with my this n cap a l. So this is an area integral again. So this can be converted to my so because of this dot n cap thing, we can convert it into a volume integral, and that's what we do. We convert it into a volume integral, and we get like this. I'm writing like this. This is also a notation to like this two underlines. So this is also a way to write second order tensors. So, convert into a volume integral. So if I know my stress, then I can easily convert this whole equation into like we can solve this whole equation. So all of these, since these are volume integral, I will like draw a slight tangent, and like we can uh, we can like understand how this converting into the volume integral helps. So we so far have this. Plus this is also a volume integral. Let's say we have gravity force. This is also volume. So since all of these are volume integrals, we can simply like assume, and this is valid arbitrary, right? We have not assumed what this volume will look like. So we can assume a very small volume, and if we continue to shrink this volume and like essentially shrink it to a point, then we can simply drop these integrals, and we have these values defined at this point, right? If we make it so small that these values are like essentially at points, we all have all these values. We have the density, velocity, stress, everything we can define at a point in a continuum, in a continuum sense. So we can simply drop this volume integral. That's why we have converted everything in volume integral, so that we can drop this volume integral and simply deal with a normal equation rather than an integral equation. So what we have here so far is this. And this definitely, this stress is what we have explored after this. So this stress is generally composed of, it's composed of two parts. One is our pressure. So this is which kind of pressure? Do you remember? Is this mechanical or thermodynamic pressure? So this is
So
our
mechanical.
thermodynamic pressure.
Sorry, sir.
So
Thermodynamic pressure.
yes, this is the thermodynamic pressure. What is mechanical pressure? It simply like stress over the three direction. So like this is a second order tensor, right? I will like if I expand it, I will expand it into a matrix. So whatever the diagonal terms we have, like sigma 1 1, sigma 2 2, sigma 3 3, if we add them up and divide by 3, that is my mechanical pressure. So this is basically the average of the normal stresses which is acting. That we will like if we have any pressure measuring device, this is what we will get, the mechanical pressure. But like we are also very interested in this thermodynamic pressure, because this first of all like has a connection with our understanding of states of like the state of matter, and like equations such as the gaseous equations, where like the density, how the density, pressure, and temperature, these are related. So it ties in with that. Secondly, this also like gives us a very like lets us decompose our stresses like this. So P here, we are assuming our pressure in this thermodynamic pressure is acting similarly in all three sides. So this is basically an average, this like average pressure, and that is itself acting in all three directions. So that gives us a nice way of working around our like equation, the dynamic equations that we are currently doing. So this is our thermodynamic pressure, not the mechanical pressure. Okay. So this part we can we can simplify here. If we put it, uh, if we put it here, it will simply reduce to minus grad P, and this you are familiar with. Plus, I will still remain with this term. So what is this tau called? This is called my deviatory stress tensor. So this is my deviatory stress tensor. And all my viscous stresses, Newtonian, non-Newtonian fluids, every such discussion comes under this deviatory stress tensor. And so where this Newtonian, non-Newtonian, and like classifying of these fluids and these things come into the picture is how this deviatory stress tensor is related to my velocity. So del u del x. So I'm not putting ij here. So any like the total distance, this tensor, how this is related to this. So this relation determines whether this is a Newtonian fluid or non-Newtonian. What happens in case of a Newtonian fluid? This is a linear relation, but it's not very simple. So here a second order tensor is there, here a second order tensor is there. So the relation cannot be simply a scalar quantity. So we have a like a larger tensor quantity, and I'm not going into those details. But in case of Newtonian fluid, what we have finally is two terms. One is our normal viscosity that we know, which is related to your shear stresses. This is related to minus. So this is related to your shear. So this velocity gradient. So I have discussed it in a previous video as well. So these are the velocity gradients. So like when you have this relation, you are talking about the shear stresses, and this shear stresses is linearly dependent on your this deviatory stress tensor using this mu, which is my dynamic viscosity. Plus, we also have another term, which is generally important if we have like compressible flows. If we have compressible flows where your normal stresses are important, where your like uh, sorry, the like it is deforming. So here normal strains are important. That's what I wanted to say. So this is del u del uh, del uk del xk. So these are the diagonal terms of the velocity gradient tensor. So diagonal terms, these are related to your normal strains. So this is related to shear strain, and this is related to normal strain. This is my viscosity. So let me just write this. And this is my bulk viscosity. So this term generally vanishes if we are not talking about uh, flows where normal strains are important, like our incompressible flows that we deal with in this course. Okay. So this is the portion of my deviatory stress tensor, and like if we put this back in this equation, we will get our like the Navier-Stokes equation, which we like use to solve different fluid mechanical problems, and like simplify a lot for various different cases and work around that. Okay, one such simplification comes when we have inviscid flows. So we just discuss about effects of viscosity and like straight away let's move to inviscid flows, but these viscous effects are actually not important. So not that important. So in our inviscid flows, we have like worked with a like very important relation that has helped us simplify a lot of problems, which is our Bernoulli's theorem. So Bernoulli's theorem, uh, what are the other assumptions of Bernoulli's theorem? Can you please say other than inviscid flows?
The 2 points are in a streamline, sir,
Yes. So the two,
between which.
yeah, uh, it is valid along a streamline. So any 2 points and at the streamline. So we have this is valid along a streamline. Other than this, any other thing?
Steady flow.
It's a steady. So what do you mean by steady flow?
It will not vary with time.
It does not vary with time. So do the particles remain stationary? Fluid particles remain stationary and they do not move. They do not vary with time. Their position.
No, supposition will vary, but the
Yes, yes.
properties, it will not vary with time.
Hmm. So what we are doing again, like a steady flow, when we are saying steady flow, we mean always mean it in an Eulerian sense. Our velocities are defined hmm, at point in space and not for a particular particle. So the particles may move around, but like what we have constant is our velocity at a particular point x comma y in the space, and it is not varying with time. So that's what we mean by steady. Okay, well, what you said is exactly correct. So, what is this relation that we have for this inviscid flows along a streamline and steady flow? We have pressure plus like half rho v square is the magnitude of velocity squared. So, like v dot v basically, and uh, we have assumed that this flow, if we have assumed that this flow is working under gravity, we have rho g. This is constant for all points along a streamline in this. So, so what we do, like now, we do not have to really worry about the differential equations that we have just written down, and we can simply like solve solve using this. So let's say like we have solved numerous problems like this. Like let's say we have like uh, means a tank like this, which has a free surface, and we want to find out the velocity which is coming out. We can easily find this using our Bernoulli's theorem. So in this case, you may say it is like how we define the streamline. So we can simply assume that this velocity is uniform in the orifice. Like this is completely mm, an inviscid flow. The viscous effects are not important. So we can simply say that since this is a free surface and this is also like means fluid particles are moving out, there must be some point on this free surface which connects to a point in uh, the outlet using a streamline. So we can simply use our Bernoulli's theorem to find out this velocity. How? We will assume the velocity of this free surface to be negligible because of the large size of the tank, and we know the pressure here. The pressure is atmospheric. Pressure at the outlet will also be atmospheric since it is like coming out. And this, what else is there? This rho gh is there. So there is definitely a height gap between these two. So the rho gh value for these 2 points will be different, and using that, we will get our velocity. So numerous other problems also can be dealt with. So like if you have any doubt, let's go to that first. Then we will like continue on the like on this discussion. Yeah, you need. Uh,
Sir, I have a doubt in
mm.
that early week lectures, sir. Can I ask?
Yeah, yes, yeah, sure.
In that force to find force on immersed surface, sir.
Mm.
Like usually the problems we solved were like we are measuring from the free surface.
Mm. Okay.
I have just one doubt, sir. If
Yes.
I take like a spherical ball,
Yes.
empty, like spherical tank or a spherical ball,
Mm.
and if I fill half with water,
Yes.
half with water, then
Mm.
I will like the other half is filled with air with atmospheric pressure.
Okay.
If I want to find the force at the bottom quarter surface, like how can I solve it, sir?
Force on the bottom surface. So, like, let me
Quarter
understand your
surface.
like question first. So, you have a
Uh,
spherical container, right? You have a
yes,
spherical
sir.
container, and this spherical container is half filled with water.
Yes, sir.
No
Then half
problem.
is air with atmospheric
Hmm.
pressure.
Okay, so air inside here as atmospheric pressure, like there is definitely no variation with height here. We go, like air for air at least. So at like water, you will still have, like if it is working under gravity, you will still have this variation with height, right?
Yes, sir. Now
Okay,
I want
what do you want to
force force on the bottom quarter surface, on the quarter, bottom quarter, right, right side.
know? Bottom quarter or this particular point,
No, sir, that surface. Like
this
if there is
this
like a
whole this whole surface.
not holes, only quarter surface. Like if there is a hinge, like a door kind of thing.
Okay, okay, understood. Okay, if you have like some door like this, which if you open and like means water will come out, so you're holding this door with some valve which will fill after a certain force. So that kind of a problem, right?
Yes, a door, or if not door, I can take it as normal surface also, no, sir.
Hmm. Understood. So what you have to do here?
So if I want to find the
Hmm.
like the force acting on it, sir,
Yes.
usually like in the problems like with search in which like in which the videos which were solved and in
Hmm.
assignment also, we were
Hmm.
directly taking the height from this free surface.
Yes.
But here
Here
it
also
is force.
we will take the height from the free surface itself. So let's say like means let's say you want to find a certain angle theta. Hmm. So at this particular point you want to find force, find the pressure. Okay, you need to first find the pressure to find the force, right? Hmm. You need to find the pressure along like at each point to find the force. So what will be the like pressure acting? Atmospheric pressure plus this one. So atmospheric pressure is also acting outward, so you will only take the gauge pressure. So this is radius is r. So so this distance, this height is r plus theta, right? So your excess pressure apart from the gauge pressure will be this r plus theta, correct? Now this pressure is acting this way. Hmm. And some other point it will be acting in like other direction depending on your theta, since it is acting normal, but you would want in your force only in certain direction, right? Are you following? Like am I answering your question? That's what I want.
Sorry, sir, can you repeat the
Yeah,
last sentence?
yeah, can am I answering your question?
Yes, sir, you said
Hmm.
we have to find force. Like I didn't get
Hmm.
the last sentence, sir.
Yeah, so we have to find the force. So how will you find the force? So in a plane surface, for a plane surface, what is happening? Your pressure is directed in your normal direction, and this normal direction is also the same direction. So if you simply integrate along the surface, you will find out the resultant force. In this case, you have a curved surface, right? You have a curved surface. Your pressure is acting normally, but this normal direction is actually changing with every point. In this case, it is acting this way. In this
Yes.
case, it is acting this way. So what you have to do is basically take the component. So in this particular region, you will calculate the force as P into dA. But again, take this component. Let's say you want to find the force in this particular component. So you will take this angle and calculate the force. If you want to find like fx and fy, then you will take this fx this direction and fy this direction, and like calculate the angle and like calculate both fx and fy. Is that clear? Like for example, in this case, you have this rho g r cos theta, but which direction is it is acting? It is acting in this direction, this particular direction. So if you want to find, for example, fx, what you will do? You will take a sin theta component. So your fx will be this into dA, whichever area this is acting. Does this answer your question?
Yes, sir.
Okay. Like, is your doubt clear?
What about Fy, sir, then?
Yeah, Fy, then you will have to take the cos component, cos theta component. Fy, you will have to take the cos theta component. So you will get, if you integrate this over the area, mind you, the like if this is a sphere, this is not a very like straightforward problem, especially for fx. So fx I have like simply taken sin theta. If it is a spherical, there will be a third dimension to it. If it is a cylindrical, however, what I have written is correct. If like you understand, right? If it is a cylindrical, I am looking at a cross section, then fx is this. If it is a spherical, then there will be definitely another component that I have to take care. Fy is definitely cos theta, even in cylindrical. So this area dA, how will you write it? It depends on whether this is a cylindrical tank or a spherical tank. Cylindrical, the problem is easier. So you will simply write your dA as some like rd theta into the width of the tank. So then you will simply integrate it along your theta. So whichever theta you want to like have your door in, so you will simply integrate it along that. You will get fx and fy. So these are two components of forces, right? These are two components. You will get fx force and fy force. The resultant of these two components is the direction of your force. Correct. And if you have a hinge, so are you following me till now?
Yes, sir, I'm following, sir.
So if you have a hinge, let's say at a arbitrary angle, like point you have a hinge, and you found out your resultant force at this particular. Let me make it a little bit more generic. So let's say you found your force to be at something like this, and this is your hinge, and the pressure that you are applying is something like this, right? Like outward pressure to keep it closed, keep the door closed. You need to apply some force to keep the door closed, right? So now what you will do, you will simply do a moment balance from this particular point, and you know how to do moment balance. So you
Yes, sir.
extend this, take this, extend this, and simply equal these moments. Okay.
So then it is equivalent to like even if the um no,
Yeah,
like
yeah. So means this is the critical case. So in the critical case where this outward force is like this inside pressure is almost about to open this particular force that you have applied. So this is the critical case. If your this force is larger, there will be definitely like you will see like doors having something like this. So it will not go this way. Like it is constant to only remain locked like this. If the outward force is larger. If the inward pressure force is larger, then this door will open and water will come. Clear?
yes, sir. Sir,
Yeah.
just the previous slide, sir, once.
Yes, sure.
So instead of like the atmospheric pressure on
Hmm.
like on top of water, if it were like some if I was applying some additional extra some if it was like a pressurized chamber, then
Yes,
also will
sure.
it be same?
No, no problem. So, like, you will, if it is a pressurized chamber with some gauge pressure like PA, So you will simply add PA in this. Like so, this rho g r cos theta. This was your pressure. So you will simply add PA to this. No problem. It won't change your analysis that much.
Then for Fy, sir?
Fy also you will do the same thing. Both of them we will do the same. Right. So your pressure earlier at a like a particular angle theta was rho g r cos theta. Now it will be PA plus rho g r cos theta. The gauge pressure we are talking about. Why we are talking about gauge pressure? Because the outside pressure is also atmospheric, right? So whatever pressure that you are like force you are calculating at the wall, like there will be also some atmospheric pressure outside the wall, which will cancel the atmospheric pressure inside. So what you need to calculate? You need to calculate only for the gauge pressure. Okay.
Okay, sir. So one more, sir. I
Yes. Definitely.
uh, like I want like is it correct or not? Like I instead of integration, I took that fx and fy as um for fx I projected it, sir. Like if it is like if it is like a cylindrical, if I
Hmm.
project it will be rectangular, no, sir, for fx.
I didn't get your what the
No,
project
sir.
means.
That as sir told that to find fx and fy for
Hmm.
horizontal force, he told we should project the surface.
Uh, so fx and fy you calculated. Both you calculate, or I didn't understand.
No, sir. Sir, as he told in the video, for vertical force, we took the weight of the water
Hmm.
above the plane, above the surface.
Hmm.
I
Okay.
asked that method, sir.
So we are not like taking the like weight like this. We are simply calculating the pressure, right? And since the curved, if it is not curved, so we don't have like the weight acting downwards like this. We have the pressure which is acting normal. Hmm.
No,
So
sir. Like,
weight is already taken into account by this rho g. Hmm. So yeah, tell me.
sir had did like two ways, sir. One integration, sir, as you did.
Yes.
Then one more, he took the the weight of the water above the curved surface for vertical force.
Okay. So let me try to understand what you are saying. So this curved surface is there, and he took the weight of this column, something like this.
Yeah. Yes, sir.
Okay, okay. Hmm. Then,
Like if I take the weight of the water column, then I will get the vertical force. Then
hmm,
for the horizontal force, he took the projection of the surface.
okay. So like in this case, like let's try to understand this. So yeah, in this case, let this be a control volume, for example. Hmm. Let this be a control volume. So if these are vertical, is any force acting on this side? Net force, nothing is acting on this side, right? Hmm. So the only thing that is acting is basically our gravity forces. So he is very correct to like say that this is means, like there will be a body force here, and there will be. Oh, okay. Let me try to draw this properly.
So I applied the same method for that. Like if I apply it,
Hmm. Let's try to understand it first. What like why this is applicable? Okay, then like then I will hear you. Okay.
okay.
Yeah. So we have this control volume. We have the weight of this fluid. So if we are doing by this control volume method, what are the we have to identify what are the forces acting on this. So this is basically control volume method. So we should think about your RTT, but your RTT left hand side everything will be zero, and you will be left with the forces. So since this is a steady problem and everything, like not only steady, this is a hydrostatic problem. So there is no velocity at all. So your left hand side will definitely be zero. So your net force that is acting on this must be zero. Okay, that is clear. So what are the forces
Yes.
acting on this? One force that is acting on this is the gravity, like the weight. We are not now
Yes.
using our Bernoulli here. We are using control volume. So we need to like if you remember in our expansion, like Bernoulli, where does this rho g term comes from? It comes from our body force term, right? When we integrate along a streamline, then like the body force term actually becomes your rho g h. So we need to take that body force into it. So what is the body force? We will calculate the volume of this particular like volume of fluid. So rho V into rho. This is our mass into G. This is the force. What is the other force? Other force is this, right? My vessel is applying another force on this particular volume.
Yes, sir.
Hmm, correct.
Yes, sir.
Now, uh, what we know that this fluid is actually like not means, this is stationary, right? So this must balance each other. Hmm. So the vertical forces that is must balance each other. These two sides are not applying any vertical forces, right? In the y direction, these two sides are not applying any forces. Hmm. So this, let's say F is this particular force. So this F, the y component of this F, so it has two components. One is this, and another is this. So this y component Fy, this must be equal to my rho Vg, since no other vertical force is applicable.
Yes, sir.
Hmm. Now, if we know this theta, if we know the theta about of this particular force, then we can also find our effects. Okay, did you get my point? But we need to know the angle on through which this force is acting. Hmm. So, if we know the theta, then what will happen? What will be my FB? What will be my FB? This will simply be uh, Fy by cos theta. So this is the like, is this what he was talking about? Can you tell me? Like let me know like what else is the doubt in this particular problem?
Yes, sir. Similar way,
Hmm.
sir.
Hmm.
In this, like, down in the Fy, sir, we are calculating the volume of water, no, sir.
Yes.
So, like in here, like it is free surface, open to atmosphere.
Hmm. Hmm. Hmm.
So calculating volume is easy. Directly, like whatever the control
Hmm.
volume I'm
Yes.
having, I will get it.
So if you have a pressurized chamber in this particular case, then you have to calculate the force on due to the gauge pressure. So there will be an additional force. Nothing else will change. So if you have a closed surface, there is no problem. If you have an additional like pressurized chamber and you have some gauge pressure PA acting on this, what will happen? You need to simply add to this pressure to this equation, this PA into this surface area. So A surface area. This you need to add. Nothing else. Nothing else will change.
So surface area of that
Yes.
curved
The
surface.
yes. Like this projected surface area. Surface area of this surface, not this curved surface, the above surface, where the pressure is at.
Okay. So then in the previous problems in which I told,
Yes, yes.
uh, here, like if I want vertical force, then the one will be the weight of that quarter water, no, sir.
Mm-hmm.
And other will be pressure into the half line, that area.
Mm-hmm. Yes.
Is it correct, sir?
Mm, yes. So, yeah. you said like this volume and this half line, right? So my concern here is how do you find out the direction? How do you find out the direction of this person? How do you find out which way your theta is? So what was the method used there? Can you recall? Because you
Like,
don't really know. You don't really know which like at which particular angle your force will be directed towards. Hmm. Because your pressure here is not constant. In your curved surface, what you have, sorry, so the curved surface that you have at higher, you have less pressure, and as you go lower, you have more pressure. Hmm. So your theta will not simply be like the midpoint of this; it will be biased. You understand? So this direction you have to find. If it is a plane surface, then it's not a problem. You know the direction. But if it is a curved surface like this, then you need to find out the direction uh, along which your forces act. Okay. Did I answer your questions?
yes, sir.
Okay. Is there any other question?
No, sir.
Okay. Okay. So like I am already up my like scheduled time. So uh, like yeah, we were like discussing about this Bernoulli's theorem and all. I would have like continued is how like we can relate this like to our head losses and that we have already discussed, and also like using our control volume analysis how we can like solve problems, and that this portion is actually very important. So here we have like already used a control volume, so some discussion has been done in this particular class, but that particular portion is very important and like it should be taken like care of. So in control volume problems, you have to identify the control volume. You have to see which kind of you have to start from your Reynolds transport theorem and see whether your transient term is playing any role or not. If it is not, then you can cancel it out. Then you have to again check whether your flux terms are playing any role or not. In these cases, the fluid is stationary, so there is no flux in or out. But in most of the problems you solve, you will have some flux coming in and flux going out. So that term you have to calculate, and also you have to understand which forces are acting. So here, if you have a pressurized chamber, you will have an extra pressure from your pressurized like air above. Otherwise, if you have atmospheric, that pressure will not be required since that an atmospheric pressure is also applied from the outside of the chamber. That's why atmospheric pressures will cancel out. Okay, so all these things you have to keep in mind. What are the body forces acting? What are the surface forces? Okay. Yeah.
Yes.
So I'm closing the session. So all the best for your like evaluations. And, okay.
Sir,
Yeah.
sir, like after this course, next which course can we take, sir? If you have any idea.
So it depends on what you are interested in. So there are
Like,
numerous. Hmm.
like here and a certain boundary layer, like we discussed, sir. Like
Hmm.
in this course, it was not there.
Yes.
So next course, is it like we should take some advanced level course?
Yeah, you have like advanced fluid mechanics you have for this. If you want to like study something which is like boundary layer, something which is close to the interfaces at like smaller scale, then you can take courses like microfluidics. Hmm. And like if you are interested in turbulent flows, you can take courses related to the that you can take courses related to aerodynamics. So this is basically a pathway that whichever area that you are interested more in, you can like delve into that. Also, if you see the syllabuses of these courses, like courses related to aerodynamics, courses related to uh, turbulent flows, and like microfluidics. So if you see these syllabuses now, from the knowledge of this course, you will be able to identify what is exactly being taught there. So that's how also you will be able to get an idea.
Okay, sir. Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you.
So this is the last session.